Welcome to this webinar on surveillance audiometry in the What Does Good Look Like series of the Health and Safety Executive Talks, sponsored by GTS MedOH and Gray's Specialist Recruitment in partnership with the Faculty of Occupational Health Nursing. My name is Rachel van Bazaal. I'm a Specialist Inspector in Noise and Vibration and a hearing scientist by background. Before I start, I would like to thank my former colleagues, Daniel Rowan and Emma Mackenzie at the Institute of Sound and Vibration Research, University of Southampton, and Jackie Patel here at the Health and Safety Executive for providing me with material for this webinar. The aim of this webinar is to explain what is required of occupational health professionals to measure hearing accurately and the importance of quality surveillance audiometry for a successful hearing conservation programme. In this webinar, you will learn what technical factors affect threshold, what procedural factors affect threshold, what the implications are for detecting a change, and why your interaction with employees matters. So why do it? Because the law requires suitable health surveillance, which shall include testing of their hearing where there is a risk to the health of employees exposed to noise, consideration of appropriate information obtained following health surveillance in the risk assessment, and the collective results of any health surveillance to be included as part of the information, instruction and training provided to employees. Or more simply, because you want to detect a change in hearing that could be due to noise exposure, take steps to prevent any further deterioration, and educate and motivate the employee to protect their hearing. The first two goals are reactive in that you're waiting for damage or responding to damage, but the third goal is proactive. This is where you can prevent damage from happening in the first place. This goal of surveillance audiometry is often overlooked, but is arguably the most important. Surveillance audiometry is about detecting a particular change in hearing, that is, a change in our hearing thresholds. We do this using pure tone audiometry, and more specifically using air conduction pure tone audiometry from 500 Hz to 8 kHz. Why pure tone audiometry? Well, it has standardized procedures, it has well-established norms, it can be conducted on most adults, and it tests the entire auditory pathway. We are often asked, why can't otoacoustic emissions be used instead of pure tone audiometry? Whilst otoacoustic emissions can be used to detect early hearing damage in individuals with good hearing, they do not provide any information about the degree of hearing loss for people who do not have them. Otoacoustic emissions may be absent because of problems with the ear canal or middle ear, and they are likely to be absent in individuals who have moderate to profound hearing loss. In addition, there is a lack of agreement on the otoacoustic emission test type, the test parameters, and the operating protocol that would be used. If a recommended procedure for an otoacoustic emission test for surveillance audiometry is developed, this will likely be in addition to pure tone audiometry, not instead of it. The test results for pure tone audiometry are recorded in an audiogram, which has a standard format. Frequency is plotted along the horizontal axis and hearing level along the vertical axis. Crosses are used for the left ear and circles for the right. It may also show a shaded region called the speech banana to help predict what components of speech may or may not be audible. This is a particularly useful feature when discussing test results with an individual to help them make sense of what they're experiencing. Hearing thresholds that are 20 dB or less are said to be within normal limits, but this is age dependent. According to British, European and International Standard 7029, which gives the statistical distribution of hearing thresholds related to age and gender, more than 95% of 18 to 35-year-olds with no history of undue exposure to noise or ototoxins have hearing threshold levels better than 20 dB at all audiometric frequencies. More than 25% of 18 to 35-year-olds in this group have hearing threshold levels better than 0 dB at all audiometric frequencies. This has really important implications for making valid baseline measurements, as we shall see. Psychophysical measurements, like the measurement of hearing threshold, are subject to measurement uncertainty. Some of this is random variation that cannot be controlled, but other sources of uncertainty are within your control. These sources include the measurement environment, the equipment, the subject, and by subject I mean the employee whose hearing you are testing, the method that you use for making the measurements, and you, the tester. In order to detect a real change in an individual's thresholds, it is crucial that you minimize the uncertainty where you can through good quality measurements. In this webinar, we shall consider each of these sources in turn. Starting with the test environment. When selecting an appropriate test environment for measuring hearing thresholds, two key considerations are the ambient noise and the potential for distractions. Now you might be tempted to ask, why do I need to measure the ambient noise? Surely an informal listening check will do. And the answer is, you do need to measure the ambient noise because you cannot measure an individual's hearing thresholds if the ambient noise is not low enough. This should not come as a surprise. The measurement of ambient noise is required if you are following the British Society of Audiology recommended procedure for surveillance audiometry, or the British, European and International Standard 8253-1 for audiometric test methods. You might then ask, what can I measure it with? And the answer is a sound level meter that can measure the frequency content of the noise in octave or third octave bands. What noise is permissible? Well, according to the British Society of Audiology recommended procedure, the ambient noise should not exceed 35 dBA, but it's a little more complicated than this. The maximum permissible ambient sound pressure levels for air conduction pure tone audiometry are defined in BSEN ISO 8253-1, and they depend on the test tone frequency range, the earphone attenuation, and the lowest hearing threshold level to be measured. So let's consider each of these in turn, starting with the test tone frequency range. Noise with energy at low frequencies can mask test tones at higher frequencies. This is often referred to as the upward spread of masking. Low frequency test tones therefore require a quieter test environment. For example, if you have a test tone at 125 Hz, you need to be particularly careful to minimize the noise below 125 Hz. The 500 Hz to 8 kHz test tone range used for surveillance audiometry permits more ambient noise. Here we have a plot of the maximum permissible ambient sound pressure levels across frequency if we use supraoral earphones. The lowest line, which is the darkest shade of green, shows the maximum permissible ambient sound pressure levels if we're interested in testing from 125 Hz upwards. The middle line shows the maximum permissible ambient sound pressure levels if we're interested in testing from 250 Hz upwards, and the lightest green line is for test tones from 500 Hz upwards. Ambient noise levels falling within the green shaded area are permitted for surveillance audiometry. So far so good. We've made it a little easier for ourselves by not testing at 125 Hz or 250 Hz. Now let's consider how earphone attenuation affects this picture. The maximum permissible sound pressure levels are based on the average earphone attenuation. Supraoral earphones give the least attenuation and therefore require a quieter test environment. But some listeners will receive less than the average attenuation, so you need to bear this in mind and reduce the ambient noise to as low as practicable. Here we have the same plot again, this time showing the maximum permissible ambient sound pressure levels for test tones from 500 Hz upwards for supraoral earphones, circumoral earphones, and insert earphones. More ambient noise is permitted for the higher attenuating insert earphones, But remember, these lines are based on the average attenuation. You should not work to these limits. Finally, we need to consider the lowest hearing threshold level to be measured. 0 dB hearing level on an audiogram is based on the median thresholds of a large group of otologically normal 18 to 25-year-olds. This means that half of those will have thresholds that are better than 0 dB hearing level. The maximum permissible ambient sound pressure levels in BSEN ISO 8253-1 and in the graphs that I've just shown you are for measurements down to 0 dB hearing level. If you are going to measure the baselines of young adults with normal hearing, you will need to further reduce the maximum permissible ambient sound pressure levels. Here we have the same plot again for the supraoral earphones and for the test tone range that starts from 500 Hz. We need to reduce the permissible noise levels by 10 dB in order to make valid measurements down to minus 10 dB hearing level. So how do you check that you are not exceeding the maximum permissible ambient sound pressure levels? 1. Measure the levels in the test room under representative conditions. It is no good measuring the levels early in the morning when the building is unoccupied if the occupancy and the consequent noise levels are going to increase during the day when testing is occurring. 2. Obtain the average sound attenuation data for the earphones. If these are not in BSEN ISO 8253-1 already, this information should be in the audiometer or earphone instruction manual. 3. Calculate the difference in attenuation between the earphones and the typical current supraoral earphone values in the standard. 4. Add the difference values to the maximum permissible ambient sound pressure levels for typical current supraoral earphone values in the standard. And 5. Compare the result with the levels measured for the test room. Here is a real-world example. You have no audiometric booth, but you've been offered a choice of 3 quiet rooms: the office, the first aid room, the lab. You know that the ambient noise level should not exceed 35 dBA. On the basis of this information, the lab looks like a plausible test environment. But is it? Here we have a plot of the ambient noise levels in 1/3 octave bands for each room. If we overlay the maximum permitted ambient sound pressure levels for the supraoral earphones, we can see that the levels have been exceeded in all 3 rooms. We have a couple of options. We either find a quieter test environment, or we use earphones that have higher attenuation. If we switch to a pair of Sennheiser HDA200 circumaural earphones, we exceed the maximum permitted ambient sound pressure levels for the office, but not for the lab and the first aid room. But this only allows testing down to 0 dB hearing level. If we have young adults in the workforce, a quarter of them will likely have thresholds better than 0 dB hearing level. If we are making measurements down to minus 10 dB hearing level, none of the rooms are suitable. Again, we have a couple of options. We either find a quieter test environment, or we use earphones that have even higher attenuation. If we switch to insert earphones, we could potentially make measurements in the office, the first aid room, or the lab. And in fact, we can minimize the ambient noise further by placing earmuffs over the inserts. The choice of test room then depends on the potential for distractions. Minimize distractions. If the subject can see other workers, vehicles, or machinery, or feel the vibrations of footsteps through a mezzanine floor, their attention is likely to wander. Now moving on to equipment. We shall consider the earphones, the audiometer, and calibration in turn. Audiometric earphones come in 3 types: supraoral, circumaural, and insert earphones. All must have reference equivalent threshold sound pressure levels, or RETSPLs, for calibration. All must have attenuation data. To obtain the reference equivalent threshold sound pressure levels for an earphone, the hearing thresholds are measured using a group of otologically normal 18 to 25-year-olds. The RETSPLs are the median earphone output sound pressure levels corresponding to hearing threshold. They define 0 dB hearing level for a particular earphone model. Here we have a plot showing the median earphone output level at different frequencies that correspond to hearing threshold for a group of otologically normal young adults. At 125 Hz, the earphone output needs to be about 45 dB for the tone to be heard. At 4 kHz, the earphone output only needs to be about 10 dB for the tone to be heard. These values are used as a set of reference values for calibration. In other words, RETSPLs specify the earphone output sound pressure levels that give 0 dB hearing level on the audiogram. The other piece of information that we need is the earphone attenuation. This is measured using the same method as for hearing protectors. The hearing thresholds for 16 subjects are measured with and without earphones in a test chamber. The attenuation is the difference between hearing thresholds with and without the earphone. The mean attenuation and the standard deviation for the group is calculated for each test signal. For supraoral earphones, the RETSPLs are available in BSEN ISO 389-1. The attenuation values for the DT48 and TDH 39 and 49 models are given BSEN ISO 8253-1. There are a couple of newer models of supraoral earphone available which are not referenced in this standard, but typical attenuation values for these can be assumed. Despite having low attenuation, supraoral earphones are easy to position, easy to clean, and tend to have robust ear cushions, if you can call them cushions. For circumaural earphones, there is only one model with RETSPLs and attenuation data in the standards, and that is the HDA 200. Unfortunately, this is no longer available. It was replaced by the HDA 300. The RETSPLs and attenuation data are available from the manufacturer, but the attenuation is not as good as for the HDA 200. However, there is another model called the RadioEar DD450, which has been proposed to be equivalent to the HDA 200. Other makes and models of circumaural earphones are available. The main advantage of circumaural earphones is that they have higher attenuation than the supraaural earphones, but they tend to be bulkier with higher maintenance ear cushions. For insert earphones, again there is only one model with RETSPLs and attenuation data in the standards, and that is for the ER3A inserts. These have now been replaced by the ER3C model, but the RETSPLs are virtually identical. Other makes and models of insert earphones are available, and in general these have the highest attenuation, but are the most difficult to fit and come with different ear tip sizes. For surveillance audiometry, an audiometer meeting the Type 4 specification in BSEN 60645-1 should suffice with one caveat. In this standard, a Type 4 audiometer is required to have two earphones, hearing levels in the range -10 to 70 dB, test frequencies from 250 Hz up to 6 kHz, and here is the caveat, 8 kHz is required in the BSA recommended procedure for surveillance audiometry and in HSE's L108 guidance document. It should also have output level control, test signal switching, and a subject response system. In other words, be mindful that it's possible for an audiometer to meet the Type 4 specification but not include all the test frequencies that you need. Audiometric equipment standard BSEN 60645-1 also requires that the instruction manual includes identification of the earphones and their RETSPLs, the sound attenuation characteristics of the earphones, and maintenance and calibration procedures and schedules. So all of this good stuff should be in the manual, even if you don't have access to it in the standards. This brings me on to calibration. There are 3 stages of calibration. Stage A, routine checking and subjective tests that should be done at least weekly, if not daily. These do not require any specialist equipment, but you do need a good pair of ears. Stage B, periodic objective checks that should be done preferably every 3 months, at least annually or whenever the earphones are replaced. And Stage C, basic calibration tests that are done after equipment malfunction or after a long period of time. The Stage A checks are the most relevant for audiometricians. For these, the only specialist equipment you need are your ears and your eyes. These checks involve cleaning and examining the audiometer and accessories for wear and damage. The earphones are the one piece of equipment that are most likely to be abused, and it is crucial that these are well maintained to ensure that your test results are valid. The earphone cushions, headband tension and swivel joints are particularly prone to wear and damage. The next step is to switch on the equipment and check the serial numbers are what they should be. Earphones and audiometers are calibrated together and should not be swapped around. Then check each earphone output is approximately correct by listening to the test tones at all frequencies at a just audible level. Check each earphone output at a high level for proper functioning, that is, the absence of distortion, intermittency and clicks. Check each earphone at low levels for unwanted sounds such as noise or hum. Check switches, lights and indicators work correctly where applicable. Check the response button works correctly. And at least weekly, perform an audiogram on a known subject to check for deviation from a previous audiogram. Stage B involves specialist objective calibration to check the frequencies of the test tones, the sound pressure levels from the earphones, the attenuator steps, and harmonic distortion. During this process, the audiometer may be adjusted to compensate for any differences between its performance and the standards. Stage C calibration includes the checks performed in Stage B, plus the additional checks of the rise and fall times of the test tones, interrupter effectiveness, and crosstalk between transducers and channels. We have now considered how to minimize measurement uncertainty by controlling the test environment and by ensuring that the equipment we are using conforms to the appropriate standards and is well maintained and calibrated. Now let's consider the subject or the worker whose hearing we are testing. For subject factors, we will consider the subject preparation, ear examination, and instruction. Before a worker arrives for the hearing test, they should have been instructed to avoid significant noise exposure in the 24 hours prior to testing. This is really important for making valid baseline measurements. If they have temporary threshold shift at the time of the baseline measurement, these increased thresholds could result in a delay in detecting occupational noise-induced hearing loss. The subject should be asked if they have any ear-related symptoms, if they are being treated for ear-related problems, or if they've had surgery involving the ears. A sample noise and health questionnaire is included in HSE's L108 guidance document. It is essential that the tester ask the subject if they have tinnitus, as this can affect threshold measurement and may require the use of warble tones instead of pure tones. Hearing aids, glasses, headwear or earrings that may obstruct the correct placement of the earphones, cause discomfort or affect sound transmission should be removed. And wherever possible, hair or scarves should not be allowed to sit between the ear and the earphone. Ear examination is important to know if it is safe to proceed with audiometry, particularly if using insert earphones. To know if you can make meaningful measurements. Again, this is especially important to ensure that your baseline measurement is valid. And it is also important to check for abnormalities of the outer ear, including the ear canal and eardrum, which could affect hearing protection use. The following has been taken verbatim from the British Society of Audiology Recommended Procedures and the British, European and International Standard for Audiometric Test Methods. Audiometry shall be preceded by otoscopic examination. A general examination should seek to detect the presence of earwax, foreign bodies, and abnormalities of the ear canal, and abnormalities of the tympanic membrane or middle ear. If obstructing wax is found in the canals of the outer ear, it should be removed and audiometry may be delayed for a suitable period. If wax is removed, the procedure shall only be undertaken by somebody who is qualified and competent to do so. The ear should also be checked for the possibility of collapsing ear canals. This is more of a problem for older adults and can be overcome by using insert earphones. The earphones, whether supraoral, circumoral or inserts, should be fitted by the tester, and the subject should be instructed not to hold or move them. The earphone sound opening should be aligned with the ear canal entrance. Incorrect placement may invalidate calibration and provide less protection from ambient noise. What this means in simple terms is that this bit should be aligned with this bit. Instructions are extremely important. An individual's response criterion, that is their response proclivity or inclination to respond, will depend on how they are told to respond to a stimulus. Your instructions need to be clear and they need to be consistent. Some subjects will think, was that a sound? I don't want to look like an idiot by pressing this button if it isn't there. Other subjects will think, was that a sound? I don't want to look like an idiot by not pressing this button if it is there. By giving clear and consistent instructions, you can minimize the uncertainty in how the subject responds each time they have their hearing tested. The recommended procedure for surveillance audiometry gives the following example instructions. I am going to test your hearing by measuring the quietest sounds that you can hear. As soon as you hear a sound, press the button. Keep it pressed for as long as you hear the sound, no matter which ear you hear it in. Release the button as soon as you no longer hear the sound. Whatever the sound, and no matter how faint the sound, press the button as soon as you think you hear it, and release it as soon as you think it stops. Having the subject hold down the response button for the duration of the test tone helps spot guessing. This brings us nicely on to the measurement uncertainty associated with the method. For the method, we shall consider the test order and timing of tones, the method for finding threshold, and other factors affecting the threshold estimate. For test order, always start with the better hearing ear as determined by the subject's subjective opinion. This helps to minimize test performance variation. Test in the order 1, 2, 3, 4, 6 and 8 kHz, 500 Hz, and then 1 kHz again. If the retest at 1 kHz is equal to or less than 5 dB, take the most sensitive value. If not, re-instruct and retest. Then repeat for the second ear. Ensure you vary the duration of the test tones between 1 and 3 seconds, and that you vary the test tone interval between 1 and 3 seconds to avoid presenting the tones in a rhythm and to make it harder for subjects to guess when a tone is being presented. The method for finding threshold starts by presenting a tone that will be clearly audible. Following a positive response, the tone level is reduced in 10 dB steps until there is no response. The level is then increased in 5 dB steps until there is a positive response. The level is then reduced by 10 dB and increased again by 5 dB until there is a positive response. The levels continue to be reduced by 10 dB and increased by 5 dB until the individual responds at the same level on 2 out of 2, 2 out of 3, or 2 out of 4, in other words, 50% or more responses on the ascent. The individual's threshold is the lowest level at which responses occur in at least half of a series of ascending trials, with a minimum of 2 responses required at that level. Let's illustrate what this means. We start at an audible level and the subject gives a positive response. We drop the level by 10 dB and we get another positive response. We keep dropping the level by 10 dB until we get no response. We then increase the level by 5 dB and get a positive response. This is our first instance of a positive response on an ascent, and it is a candidate for threshold. We then drop the level by 10 dB and increase it again by 5 dB and get another positive response, but at a different level. This is our first instance of a positive response at this level on an ascent. We then drop the level by 10 dB and increase again by 5 dB, but fail to get responses at the levels we did previously. Instead, we get a positive response, but at a different level. This is our first instance of a positive response at this level on an ascent, and it is another candidate for threshold. We then drop the level by 10 dB and increase again by 5 dB, where we get a second instance of a positive response at a particular level. As we have 2 out of 3 responses at this level, this is our estimate of threshold. You should not expect any individual to respond perfectly reliably unless that person is a robot. If they did, there would be a clear level above which you would always get a positive response and below which you would get no response. The probability of the individual responding to the tone would either be 0 or 100%. In reality, there is a region of uncertainty where an individual sometimes responds to the tones, but not all of the time. Audiometry attempts to estimate the level at which the individual responds positively 50% of the time, and it attempts to do this accurately and efficiently, but there is a trade-off between these. The probability of getting positive responses for different tone levels is plotted on a curve, going from 0% for an inaudible tone to 100% for an audible tone. This is called a psychometric function, and threshold is defined as the tone level that gives positive responses 50% of the time. Every measurement has uncertainty due to internal noise that cannot be controlled, the plus or minus 5 to 10 dB grey area. Internal noise is partly neural noise, variability in how the auditory system detects and codes sound, and central noise, variability in the individual's attention and response criteria. The steeper the slope, the less internal noise. There is evidence showing that children have shallower slopes than adults. The estimate of threshold depends on the type of method used. For example, the method can be varied to estimate a different point in the psychometric function. The step size, whether you are using 2 dB, 5 dB or 10 dB steps. The tone length. Thresholds get worse for tones that are less than half a second in duration. And response bias associated with ascending and descending series. For example, the tendency to continue responding to tones of decreasing intensity when they are inaudible. Manual and automatic fixed frequency audiometry can give similar threshold results if the method used is the same. The automatic sweep frequency Bakerji tracking method gives thresholds that differ from fixed frequency audiometry by about 2.5 dB. Our final source of measurement uncertainty is you, the tester. The tester can introduce measurement uncertainty in a number of ways. Here we shall consider individual behavior and bias, professionalism and competence. Tester behavior and bias that can influence the subject's responses include verbal communication, For example, the clarity and consistency of your instructions to the subject. Nonverbal communication, for example, looking up at the subject every time you present a tone which could cue them to respond. Differential treatment, for example, taking more time with or being more friendly to a subject because of their seniority or because they're the first subject of the day. Expectation, for example, giving the subject the benefit of the doubt based on their previous audiogram or your assumptions about their hearing based on their age, sex, or job. And lack of vigilance, for example, failing to spot a button press or a data anomaly. It happens to everybody. Our vigilance naturally varies throughout the day. Perceived professionalism will influence the subject's engagement with the test and with the hearing conservation program. Professionalism is signalled by the tester's communication. Effective communication is essential for instruction and motivation. Appearance. The subject will have less confidence in you if you are not dressed professionally. Attitude. For example, how interested in and respectful you are of the subject. Demonstration of good practice. Showing that you have selected an appropriate environment, you have the right equipment, you are controlling infection, using good technique, and are taking care to record and report. Adherence to ethical practice, that you are demonstrating integrity, confidentiality, and are prioritizing the workers' health and safety. And competence, showing that you clearly have the knowledge, skills, and ability to do the job. To underscore how important your professionalism is, I have included this quote from Royster from a chapter she wrote for the noise manual. Threshold measurements can easily be 10 dB more sensitive if the subject concentrates on listening and responding compared to the same subject going through the motions. Employees correctly interpret the audiometric monitoring situation as reflecting the employer's degree of commitment to hearing conservation. If you show disinterest, if you haven't bothered to find an appropriate test room, if you don't demonstrate good practice, the employee will perceive surveillance audiometry as a tick box exercise. And not only will this affect their test performance, making it harder to detect any change in their hearing, it will affect how much they buy into the hearing conservation programme. The British Society of Audiology recommended procedure for surveillance audiometry states that such tests should only be carried out by those who have received appropriate training in accordance with BSA minimum training guidelines surveillance audiometry. The recommended procedure for ear examination states that the examiner shall be competent or supervised by someone who is competent in ear examination for the purpose in hand. Competence should be evidenced by sufficient and relevant training, experience, and assessment. The minimum training guidelines for surveillance audiometry recommend that surveillance audiometricians undergo refresher training or competency review every 3 years. The minimum training guidelines with syllabus can be downloaded for free from the bsa.org.uk. What does this all mean for detecting a change in the audiogram? Recall that every measurement has uncertainty that cannot be controlled, the plus or minus 5 to 10 dB grey area. This means that the difference between subsequent measurements must be greater than or equal to 10 dB at any individual frequency to be meaningful. Worse, if you have not controlled all the other sources of uncertainty. Sources of uncertainty that you can control include the measurement environment, the equipment, the uncertainty you introduce as the tester, some of the subject uncertainty, and the method you use for making measurements. It is your job to minimize the measurement uncertainty that can be controlled so that results can be compared across time and space. That makes it possible for you to compare an individual's audiogram to their previous audiograms, and for valid comparisons and audiograms to be made when there is a change in occupational health service provider or when the employee changes job. This is my final slide before I come to references and resources, and I want to share 2 quotes with you that sum up why your interaction with workers really matters. In industry, hearing conservation programs can be nominally compliant and accomplish little, or they can be meaningful and prevent hearing loss. The contact between the audiometric technician and the employee at the time of the annual audiogram provides the single best opportunity to influence that individual's behaviour regarding the hearing conservation programme. Remember, 2 of the goals of surveillance audiometry are reactive. If you are only doing these, you are merely waiting for damage to happen. You also have the ability to prevent damage. These are the references that I cited in this presentation, and you can look through these in slower time by pausing this presentation. For accredited training, check out the bsa.org.uk. There are training and refresher courses coming up soon in surveillance audiometry. The recommended procedures are also available for free to download from the BSA's website. The standards most relevant for surveillance audiometry are listed here and include the standards for the audiometric test method, audiometric equipment, reference equivalent threshold sound pressure levels for supraoral, insert and circumoral earphones, and the measurement of earphone attenuation. There are lots of good books out there relevant for surveillance audiometry. I particularly like the Noise Manual. My version of it shown here is the revised 5th edition, but there is now a 6th edition. Another useful reference book is Occupational Audiometry, Monitoring and Protecting Hearing at Work, which is written for a British audience. It is a little out of date now, but the material on pure tone audiometry and otoscopy is still very relevant. The regulations and guidance relevant to this webinar are the Control of Noise at Work Regulations 2005 and HSE's L108 guidance on the regulations document, which you can download from our website. Finally, the contents of this webinar include material subject to Crown copyright and material from the University of Southampton, who kindly granted permission for its use.